Good morning. I'll present a few approaches we've been taking to analyze spectroscopic and photometric data, and specifically focus on the aspects that have to do with outlier detection. But broadly speaking, I think outlier detection is an element in a wider array, and I'm going to approach this from a probabilistic perspective, which means I need some form of model in which I can run my outlier detection. And I'll do this by introducing a two ways. So this is a piece of an architectural diagram for a neural network architecture, and I would like to point out one thing. This is the forward generative path, which means that we start from some kind of lower dimensional description. Think of these basically as representing the physical properties, the type of in our case, it's galaxies, but you could run this with stars or other things you have a spectrum of. So basically like a description of the type of an object. And that goes into this kind of red box. And that's typically rather low dimensional. Think of things like stellar mass and kind of metallicity and other things for a galaxy. But then because we observe it at some different redshift, or if it were a star at some different sort of radial velocity, there's also another operation, the redshift here, that goes into it and takes the output of the decoder, which is a rest frame model, and moves it to the observed redshift. You can also apply some kind of resampling to adjust it to the specific the specific sampling of your spectrograph. And these operations are all known analytically. We don't need a neural network to learn them. Hence, they're sort of factored out in their own operation. I use a neural network to describe this generative path. But in order to analyze data, I also have to get into this. And that means that I need to have an analysis model that ingests an observed spectrum, uses an encoder to extract all of the type information, and on top of it, because it needs to give these latents in rest frame, it also needs to be agnostic about the redshift of that source. And I can go into details of how we have done that, but it's an attentive architecture, it's an attentive convolutional architecture, and I can tune it in such a way that it basically scans the wavelength ranges for different features, and that's what makes it redshift independent. So what we get out of this is a low-dimensional galaxy spectrum model with a generator, which means that I can look at how the results of this thing look like. And you can see that because I'm observing at different redshifts, this model predicts aspects of a spectrum that actually haven't been observed directly. So hang on. Is this thing working? No. Okay, you can see in kind of the second panel on the top, it predicts an O2 line that isn't actually observed, and that it has that because it has seen that amount of O2 emission in cases when there's also strong H alpha emission, as you can see on the right. But because this generative model has like explicit resolution changing in it, I can do internal super resolution, for instance. So here we use the Sloan galaxies, but we oversampled by a factor of 2. And now we can actually resolve the O2 doublet, which is not visible in the original data. And so the internal model has that. You can make a test that the recovered O2 lines are actually consistent with the S2 line. That's the same physics governing both of these doublets. And you can see the height of these lines is exactly as we expect, despite the fact that this model has never seen the O2 doublet clearly at all. However, the main important thing is that there's a latent space, and you can start to interpret that latent space. So this is now work by Yan Liang, who is here and has a poster somewhere. And so you can talk to her about a lot of the slides that I will be showing. The latent space is now clearly structured by by redshift, as you can see left panel, then by kind of stellar mass, by star formation, specific star formation rate, and you can even pick up aspects of the dust. But that latent space, this is a two-dimensional projection of a higher dimensional latent space. We use 6 dimensions to represent the galaxy spectra. Doing outlier detection in this is reasonably hard. Instead, we are doing something else. We are not using a variational autoencoder. I have my reasons for that. I can explain. If you're a fan of variational autoencoders, meet me. I would like to kind of talk you out of it. So instead, what we are doing is we run a conventional autoencoder, so encoder, decoder structure. The latent space is now not constrained by anything. It doesn't have to be Gaussian. And instead of doing that, we attach a normalizing flow to the latent space after it has been trained. So there's no penalty during train. And what that does is allows us to make a simple mapping between a Gaussian and the target distribution, the latent space, however it's distributed. Now I can ask questions, namely, how probable is a specific sample according to the latent space distribution? So how far out in the tails is it if I'm looking for outliers? And I can do this regardless of how complicated my latent space distribution is. Here's an example of doing this in the Sloan main galaxy sample. And you can see like the Black is the data, red is the model. And what you can see here is the fit is actually pretty good, even for outliers. So these are the top outliers that we found in the Sloan galaxy sample. Number one is because that's an interacting galaxy, so you're picking up light from multiple sources. Number two, I think that has double emission lines. So there's kind of some velocity component going away from us, some going towards us. Next one is actually a star or probably a superposition of a star and something else. And the last one you can see is heavily reddened. You can see how the spectrum tilts to the red. These came out, we didn't search for them as a class or anything, right? We didn't search intentionally for them. We just asked what is low probability in latent space. And these are the highest values or lowest probability values according to the normalizing flow. We've done the same thing in DESI. The primary one is actually a superposition of two stars, but we also found these are from the Bright Galaxy survey. We also found number three, as you can see, is just outright a star. It's just a star. There's nothing double about it. It's nothing special about it, but it is actually by Red Rock classified as a galaxy. The reason is that I think Red Rock's stellar templates are not quite as good as they need to be, and they give a lower fit for the star class than they give for the galaxy templates. Hence, it ended up as being spectroscopically classified as a galaxy. So what is interesting about these outlier detection is you can see a bunch of things that are instrumental, right, or kind of have to do with the processing of the data. And it's useful to provide very fast feedback on something that doesn't quite work. And in this case, it took us basically 1 day to run this. Actually, it took us almost all of that day to just get the DESI data, and then a little bit of time to train this. And then, as Josh said, right, it's much harder to interpret these things. It took us about 3 weeks to go through all of the outliers and find out what they are. But it's very sensitive largely to sort of bulk properties being changed. And the reason for that is because we use an encoder that looks at the entire spectrum and compresses its main features. And if there's a bulk feature that is wrong, like this rise of the star on top, the fact that it rises towards the red is the thing that is wrong about it. Like stars would not do this. They would have stars of a sufficiently high temperature would not have that red tail. Brings up an interesting question, namely, how do we find those outliers? How do we know what is outlier-ish about the outliers? And so we have a work with Jeff Shen on doing feature attribution. And what we're basically doing, I don't go into details, but I can briefly show you the approach, is we take a baseline spectrum that is a spectrum that looks relatively close to the one that we are looking at. We remove one part of it and replace it by the actual observed spectrum, as you can see from the top. And we are asking the question, how does the probability of my normalizing flow changes under that change of feature? Because if it changes a lot, and then the feature that I've just inserted was apparently important for it. So you can find kind of in an automated way, you can scan sort of this and find different values or different regions that seem to be largely responsible for that outlier score. Jump over that and move to Galaxy Photometry because I'm not having much time left. Here's a different generative model. What you have here is a generative model that actually starts from the physical parameters such as metallicity and star formation rate and others, and generates a spectrum. Then you degrade that spectrum up to the broadband or narrowband photometry, whatever filter set you have, in order to predict the photometric measurements. The problem is if you want to sample through this, if you want to find the parameters, here like is a model with 11 parameters that was made by Chang and Han. If you do that, then you kind of run hours to do the evaluations on a single object. That's just not feasible. We need to scale this up to billions of galaxies. An hour per object is not doable. Even a minute per object is not doable. So what we did is use a normalizing flow. You can have conditional normalizing flows that says that you describe the distribution of the parameters given the data. They do this very well. Now we have evaluations of 1 second instead of something like 10 or even 100 hours in some cases, depending on how complicated the model is you're sampling from. This can be done with broadband photometry. Obviously, I showed you the way that we can encode galaxy spectra. We might as well do this for spectra, and that application is coming. The code for that is public. You can get it up on GitHub. But there's one thing that we found during this study, and that is there are objects in the sample where the photometry is not explainable by the forward model. So here's an example. The gray contours show the training data. That's the data that the SPS model, this forward model, can actually generate with any value of its parameters, or actually within the priors of those parameters. And there's a population of galaxies that are labeled in blue here, blue dots if you can see it. they are too bright in the blue and too faint in the red. So their spectrum is not consistent with anything we can generate. The reason is these have strong emission lines, and so the photometry is really heavily bluer than you would think. And these SPS models just don't like strong emission lines. They just can't generate them. So if you then try to run inference on an object that comes from that population, you run your normalizing flow in extrapolation mode. So you run it outside of its training regime. That's never a good idea for neural networks. So let's not. And that means that we have to find outliers in the photometry. And there's the question, what is an outlier in photometry? And it is the difference in this case, a existence of a different populations of galaxies compared to our expectation from the forward model. So what you see here is that we train a distribution, this is a small code that computes a self-organizing map out of the original training data. Let's use our simulation of SPS to define that training set. And what you get is a distribution that can be tuned to be very flat. That's what a sum wants to do. Now we ingest all of these other actual observed galaxies. You have to add noise on this and realistic levels on the training data. Then you can do the same thing with your test data. That's the actual observations. And you can see the distribution is not flat. There are regions that are overemphasized, as you can see here in this difference contour, right? There's red are places where the test data has more samples than the training data, and blue is the other way around. So what you can see here is this large group here, this large red group, is exactly the group that I've just pointed out. So you can sort of identify these regions in a relatively straightforward manner as over-densities of your test data against the training data. And this is a very simple kind of approach that allows you to do that. Let me end on kind of a few notes about what outliers are not, since we're kind of dealing with outliers and rare gems. They're not a class. There's many different ways you can be kind of an outlier. So like enforcing something of a classification is not really the point. They're also not quantifiable. That means that they're hails from some distribution. And that means that their description is really hard to sort of generalize and estimate. They're just not well understood. And they're also unexpected, which means that something like completeness and purity is completely ill-defined even as a concept. They're not self-evident. The detection of outliers might be hard, which is what we're dealing with here, but the interpretation is even harder. This is why it took us like 3 weeks to go through the list, and we needed experts. And they also ideally like not boring, right? We do this because we want to be surprised. That means that in my view, the way that outlier detection should be seen is in aiding this effort. Right? It is like if you have to dig through gold manually, then this is very kind of labor intensive. What I want from an outlier detection is some automated scheme that looks for most of the data, filters out what is not surprising, and tells me the things that are surprising. But it doesn't take out the human out of that loop. The machine will not tell me why something is kind of not as expected, why it's an outlier. We have to do this ourselves. But like it's a really good example of a sort of a human machine collaboration that can actually be really, really beneficial. And I would say it's necessary. I'll stop with showing the people from my group who have done most of the work that I talked about. Thank you.